Bismillahirrahmanirrahim. Good evening, everyone. Today let me say, not structure, at meeting number two about the effect of the different three centering temperature on the doping perovskite structure, what the effect on the structure properties about the grain size, something like that, and the magnetization properties. Here at scan electron microscopic analysis at meeting part one was talking about the atmosphere's microscopic image and illustrated some different grain size, nanoparticle size from before the centering temperature at 600 CDZ didn't reach more than 200 nanometer, but after increase the temperature from 100, 1,200, 1,400, it's reached at 1,200, it's reached approximately 800 CDZ. That's mean multiplied to 4 times, and at 1,400, it's reached something like 1.2 or 1.4, but micrometer. That's mean a huge increasing in the grain size, and talked about the effects on the doping ratio on the grain size, not a huge effect, not a huge change by increasing the doping ratio. Now let's come back to silicon electron microscopic analysis at 1,000 CEZ, 1,200, 1,400. Some change in the grain size at all of these three different temperatures. Let me change to the next slide, please. Yes. At first, the doping ratio was equal 0.05. Here, equal 0.25. Some increasing in the grain size. It's very clear at the last image at 1,400 CZ. Here, all of these together. Here at F, the researchers reached a huge grain size, a bigger grain size number. Here, the feature are the grain size increase with the increase in the centering temperature, like I said before. Energy concentration level makes almost no significant change in the apparent structure for the centering temperature up to 1,200. Not significant change. That means we have some change, but little. We can't say it's that has effect on something. Little change don't has a huge opportunity to can do some changes. However, but the situation is different at 1,400. Centered samples morphologies are quite different. Here, now let's do ratio between C, that's mean to doping ratio was equal 0.05 at 1,400 at the same temperature, but with the second doping ratio equal 0.25, a quite change between these two pictures about the grain size. It has period structure. C has a period structure. F has a grainy structure with a grain size. Let's come back to C, period structure. Here, it's a period structure to the doping ratio equal 0.05 at 1400. At F has grainy structure. F here at the, like I said before, at doping ratio equal 0.25 at the same synthetic temperature. Various structure, grainy structure, up to 20 millimeter. The small grains seen in figure 3F between large grains, talk about these. The small grains seen between large grains were found to be manganese oxide. That's mean some another material. We can say impurity between these big grain sizes. Here, it's a higher magnified scan electron microscopic image of the simple centers at 1400. That's mean specifically to this image is magnified to more times. You can reach picture like that. Sorry, not to doping ratio equal 0.25, but to doping ratio equal 0.05 to this, to Perrius structure. Yes, to the Perrius structure, to this one, by using scanning electron microscopic technique, magnified this picture to too much times to be like that. Higher magnified silicon electron microscopic image of the sample centered at 1400 CZ to this doping ratio. Particle with about 1 micro, well, not, it's bigger than nano because here it's equal 10 to force minus 6, not to minus 9, occupy holes. These particles attract the holes with the same size, about 1 micrometer, and shape. These particles has some critics, some, well, we can't say it's advantage or disadvantage, but some has some characteristic, because that these small particles, approximately 1 micrometer, can attract the holes with the same shape and size. There are also some vacant holes which saying that they have lost their own particles. That means some holes will be maybe empty, that they have lost their own particles. It is possible that these particles are lanthanum oxide, manganese oxide, maybe, or which are detected in X-ray detection pattern of this. This image, like I said before, is magnified more time to F picture, about 1400 CZ centigrade temperature to doping ratio equal 0.05 silver. Now let's talk about X-ray differential analysis. At figure 6, the change in X-ray pattern as function of centric temperature to all of these different doping ratio. The perovskite phase needs manganese to emanate. It's important note. Perovskite without doping is isolated and antiferromagnetic. Perovskite phase needs manganese to emanate. Without manganese, will not emanate. If all available manganese goes to compose to produce manganese oxide, what will happen? Like I said before, without manganese, perovskite phase will not emanate. Then no perovskite occurs, leading to the formation of metallic. That means we'll have another formation metallic. This formation metallic is silver and lanthanum simultaneously or continuously, which one do you want? Here, because the perovskite phase without manganites will not emanate, that's mean when the available manganites, all of the available manganites goes to compost to produce the manganite oxide. That means we don't have any perovskite. Leading to what? Leading to produce silver and lanthanum manganites. Here, if some manganites more than a critical value, what will be happening? Here, when we don't have manganites, but here when some manganites, but more than the level, appropriate level, appropriate number, appropriate amount, was to compose the manganite oxide, what will happen? Then some lanthanum oxide would have to form along with manganite oxide. When we have manganite more than appropriate level, then the silver will, then some lanthanum oxide would have to form along the manganite oxide. Lanthanum oxide will have to form along the manganite oxide. Here, small amount of Ag ions introduced in the parent compound has been replaced with some ions and changed the critical structure. Here it's important because it's work to change the crystal structure. Small amount, not a huge, not a big number or amount of silver ions introduced to us what? Introduced to us the parent compound has been replaced with some lanthanum, some rechange between lanthanum and the parent compound, between some amount of parent compound with lanthanum ions. That's what makes some change in the structure. At these two huge sintering temperature, Ag, the silver starts to flow out, to run of the parent compound, bringing what to us when these huge two differences in December, the silver will start to run to the parent compound, bringing the structure back to the original PNN space because the silver run out from the use internal temperature. This compound will bring it again to the PNN space group again. At the huge one, at the huge internal temperature, 1400 C, consisting of some impurity phases such as manganite oxide, lanthanum oxide beside the perovskite phase. That's mean at the huge internal temperature, they have impurity beside the perovskite phase. These impurities are lanthanum oxide, manganite oxide. These X-ray diffraction straight to us. The curves started from 1,000, increased to be like that until 1,400. A doping ratio equal to 25. The simple stain to hold the R3S structure with Ag replacing lanthanum, the parent compound, and small amount of additional Ag in the metallic form. At the bigger sintering temperature, the doping element contained with the whole material drops to less than 100%. Lesser in perovskite phase, and structure grain falls back to the original P&M space at the huge, the bigger sintering temperature. Drops, the whole materials drops to less than 100% lesser in perovskite phase, as structure grains fall back to its original shape, original space equilibrium. Here, by using this periodic table, the researchers could prove the parliament structure didn't change or didn't face a huge change. There is no systematic change in the lattice parameters, and the unit cell volume of the same thing, the unit cell volume didn't change too. All the cell walls which fall into the same space group, then the centering temperature is well above 1000 Celsius. In some manganese oxide appear as a secondary phase in the matrix. At the lesser one centering temperature, the manganese oxide appears as secondary phase in this matrix. Here now we are talking about the pure temperature. When the pure temperature is near from or around from the room temperature, that means our works are better. Okay, here at the 1000 centering temperature, the pure temperature is nearest from room temperature. Here, approximately 287, but the other is far away from room temperature. This can say the pure temperature here is less than 200, here is less than 150 Kelvin. Don't see easy, that's mean it's far away from room temperature. That's mean the better situation is on the 1000 Celsius. Now let's take a look to another slide. Here at doping ratio of 4.25. Here at doping ratio equal 0.05 at centered at 1400 Celsius, the pure temperature is more than 100 Kelvin, something like need to 200 Kelvin to can reach the room temperature, because that it's temperature far away from our room temperature. Let's take a look to the next slide because it's better and easier to illustrate. Here, the pure temperature at 1400 centigrade temperature equal 115 Kelvin. Now, at doping ratio equal 0.05, here it's approximately 287 at 1000 at the first centering temperature. At the first centering temperature at doping ratio equal 0.25, it's near from room temperature. But to all of these two images, by increasing the pure temperature, by increasing, the centering temperature, the pure temperature be far away from room temperature. That means it's disadvantage here. The pure temperature increasing with increasing the doping ratio. The pure temperature when increasing the pure temperature. The doping here, yes, like I illustrated, like I explained before, when I was talking about the pure temperature, all of these three lines, yes, the pure temperature increasing with increasing the doping ratio, from where the researchers found that, and from where could prove that, from these two images, from these two curves, by increasing the sintering temperature, by increasing the doping ratio, the pure temperature be near from room temperature more, by decreasing and decreasing with increasing the sintering temperature, by increasing the, like I said before, increasing the sintering temperature, pure temperature, decreasing more and be far away from room temperature more and more. Sintering temperature increases the silver ions monovalent bonded to perovskite phase, mainly the perovskite phase as metallic. When increase the sintering temperature, Ag ions bonded to the perovskite phase may leave, may run, may far away some perovskite phase as metallic silver. Casing what? Casing and increasing in the amount of non-magnetic phase or disadvantage, such lanthanum manganese oxide, lanthanum oxide. Okay, when increasing this, some explaining about what happened when or why happened when increasing the sintering temperature, the cure temperature decrease and be far away from room temperature. Because the ions, silver ions or doping element ions, here it's silver, bonded to the perovskite phase may leave, may run away from perovskite phase as metallic silver, casing what? Casing an increase in the amount of nanomagnetic phase. On the other hand, an increase in Ag content perovskite phase casing the ferromagnetic order. That's mean by increasing the doping ratio, discourage the ferromagnetic order. It's an advantage, is an active thing to make the ferromagnetic ordering be stronger and stronger at high temperature. The Ag ions introduced in the perovskite phase substitution lanthanum ions, resulting sum of manganese 3+ ions to become manganese 4+ ions. That's mean double exchange ratio. Yes, when the electrons can jump from side to side, from manganese to manganese, by use the oxygen-like bridge, like I explained before. Ions proportional the substituted Ag ions concentration and the charge ordering existence of manganese in two valence states plays a critical role. The charge ordering existence of manganese in two valence states. What does mean valence state? That's mean we have in this structure, in this situation, two empty states. The charge or existence of manganese, the charge order, in this empty states, in these two empty places, has an important rule on the magnetic properties, has some active on the magnetic properties to this perovskite. Here, Ag introduced in the parent perovskite structure increase the manganites 4+3+ ratio favored by double exchange mechanism, like I said before. Elevated center temperature casing silver manganites, silver ions, monovalent, mono+ ions, to leave perovskite structure, leading a decrease when the Ag 1+ run away from the perovskite. That's decreased the manganites 4+3+ ratio. What that means, it's a disadvantage, we can say, or bad thing, because when decrease the manganese 4+3+, that means the magnetic properties to this perovskite, doping perovskite, will decrease, since the initial composition have lanthanum deficiency with to Ag substitution. Formation of non-ferromagnetic phase such as metallic, Ag, silver, manganese oxide, and lanthanum oxide is possible when Ag doesn't hold to the perovskite structure. Here, the important note is here. In these compounds, maximum solubility of Ag ions and the lanthanum manganese oxide perovskite decreases solubility to this doping element, decreases with increasing the sintering temperature. Thank you so much. Have a good day, and our meeting is done. See you in the next meeting. When and where, I don't know. Have a good time, and thank you about your watching and your listening. Let me close this.